You ever stop and think about how the powerful roar of a jet engine and the quiet hum of your refrigerator are actually related? Well, they are. They're both playing by the exact same set of rules, the fundamental laws of thermodynamics. Today, we're going to pull back the curtain on these incredible rules that secretly run pretty much everything.
So let's just dive right in. How in the world does an engine take something as simple as heat, just from burning fuel, and magically transform it into the kind of raw power that can move a car or even lift a massive airplane off the ground? Let's find out.
The whole secret, the key to unlocking how that engine works, is all wrapped up in the science of thermodynamics. This is the branch of physics that explains how heat and energy really get things done in the universe.
Now, to really get this, you kind of have to shift how you look at the world. So picture a bullet hitting a wall. A physicist who studies mechanics, they're going to care about the bullet's motion. But a thermodynamicist, they're looking at something different. They're looking at the state of things. They're asking, okay, where did all that energy go? How did it transform from the energy of motion into heat? And what did that heat actually do to the molecules in the wall? You see, it's all about following the energy's journey, not just the object's path.
And if we're gonna follow that energy journey, we need to meet the three main characters in our story. That's heat, work, and internal energy.
First up is internal energy. Just think of this as all the hidden energy packed inside an object. It's all the microscopic wiggling, jiggling, and vibrating of every single molecule. In short, it's the energy that a system has.
Next is heat. And you gotta listen closely here, because this is a really crucial distinction. A system doesn't have heat. Heat is what we call energy in transit. It's the process of energy moving from a hotter place to a colder place. So it's an action, not something you can possess. And our third and final player is work. This is the other main way that energy gets from one place to another. And it's what happens when that energy transfer causes some kind of organized mechanical motion, like a piston firing in an engine, or you lifting a heavy box. That's work.
Okay, so we've met the whole team. Now it's time to learn the first, and honestly, the most important rule of the entire game, the first law of thermodynamics.
The first law is really just a fancy way of saying something you probably already know, the law of conservation of energy. It's a rock-solid universal truth. You can't just create energy out of nothing, and you can never, ever truly destroy it. All you can do is change its form. Go ahead, try it right now. Rub your hands together really fast. Feel that warmth? You didn't create heat from thin air. You just converted the mechanical energy of your movement into heat energy. The total amount of energy in the universe is still exactly the same.
Here's a really simple way to think about it. Imagine your mom gives you $100 for groceries. That $100, that's the heat you're adding to the system. You go and spend $90 on food. That food increases the internal energy of your kitchen pantry. And that $10 you have left over, that's the amount of work you can do, like, I don't know, buying yourself a coffee. Every single dollar, just like every bit of energy, is perfectly accounted for. And of course, there's a simple little equation for this. The heat you add to a system, that's delta Q. It has to go somewhere. Part of it is used to change the system's internal energy, which is delta U. And whatever's left over goes into doing work, delta W. It's a perfect balance sheet. Nothing ever just disappears. So wait a minute, if energy is always conserved, does that mean we could build a perfect, 100% efficient engine? Well, not quite. It turns out the universe has this kind of unavoidable energy tax, a fundamental rule that makes perfection totally impossible. And this gets us to the really critical question. Can we actually build an engine that takes all the heat energy we feed it, that delta Q, and convert every single last bit of it into useful work? And the answer from the universe is a hard, unequivocal no. It is absolutely forbidden, and is forbidden by another one of these unbreakable cosmic rules, the second law of thermodynamics. So, in plain English, what the second law is saying is that you can't just take heat from a single hot source and turn all of it into work. It just doesn't work that way. You are always forced to dump some of that heat into a colder place. This rejected heat is what we call waste heat. And it's not some design flaw, it's an absolutely unavoidable part of how any engine works. But here is the truly beautiful thing about these laws. They are perfectly symmetrical. If you run an engine's process in reverse, you get another machine that you almost certainly use every single day. That's right, a refrigerator is just a heat engine running backwards. It's amazing. A heat engine lets heat flow naturally from hot to cold, and that process creates work. A fridge does the opposite. It uses work, in this case electricity, to force heat to move the unnatural way, from the cold space inside the fridge out into your warmer kitchen. It's the same law, the same physics, just flipped on its head. So this leaves us with one last big idea to chew on. The first law tells us that energy is forever, it's never really lost. But the second law tells us that some of that energy always ends up as unusable waste heat. Which begs the question, if that energy isn't destroyed, where does it all go? What's its final destination? And that question, my friends, leads us down an even deeper rabbit hole into a huge concept called entropy, and maybe even to the ultimate fate of the universe itself.